Thank all of you for your attention, especially all of your enthusiasm, your great questions. I really love doing this, and you guys remind me through all of this interaction why it's so much fun to do physics. So I'm really grateful, and it's been an incredible experience to get a little window into your amazing country also, just in this beautiful campus and everything. So in this final lecture, somehow miraculously my plan is held together and we're right on track. So today I want to take all of this work we've been doing and try to wrap it up in a nice bow by really trying to understand the physics underlying this question that I keep asking over and over in these lectures, namely, are there any interesting theories that live in this space where you're forced to use the HEFT description, okay? In other words, what we're really trying to get at is now we have this criteria that we discussed last time, which tells us whether or not a SMEFT exists given a HEFT Lagrangian expressed in terms of K, F, and V, okay? And again, just to put this in context, you know, from a model builder's point of view, from the UV, we tend to think about beyond the standard model physics in terms of SMEFT. Typically, for example, today we're going to talk a lot about matching calculations or the results of matching calculations. And when we do those matching calculations, we typically do them in SMEFT, right? We're at high energies, we turn off the VEV of the Higgs, and we do the matching in terms of capital H, not little h. Of course, nothing stops you from matching in terms of little h, it's just harder, okay, technically harder. So there's lots of reasons why SMEFT, the theories that live here, are the ones that we are sort of more studied, okay? But it leaves this question, well, what lives here? Is there anything interesting? Are we missing anything in particular if we are just focusing our attention on SMEFT? So that's what I want to address today, and I want to address it by discussing the physical implications of these criteria. So just to remind you, we have this first criterion, which is the presence, which tells us where there's this O4 invariant fixed point, namely the place on the manifold in HEFT where we could write linear coordinates that look like SMEFT and where we potentially could define a SMEFT expansion. But it's not enough. We also need to satisfy analyticity requirements. So we need the functions that live at H star to have convergent Taylor expansions, okay? Basically to be polynomials. And we also have this additional very geometric criterion, which is that we compute the Ricci curvature at the point H star and make sure it's finite, okay? So I want to provide you with one example, and then I'll point you to the paper for a few others, where we're going to, in particular, we're going to investigate the meaning of this, okay? What is this telling us about the classes of theories? When this condition fails, right, what are the models that that's probing, okay? Any questions about the big picture? Yeah, please. No, this is supposed to mean, so the distances here don't mean anything, okay? This is really just to say that the HEFT description encompasses SMEFT and therefore it also encompasses the standard model, right? So I could always, there's nothing stopping me from defining the standard model directly in the physical vacuum, right? That's really what HEFT is. HEFT is the definition of the EFT in the physical vacuum directly. I could do that with the standard model, right? It's just then I'd have to work harder because, of course we all know, right? Using SU3 cross SU2 cross U1 to organize the terms we write in a Lagrangian and so on makes it pretty easy. If you had to do everything in terms of the nonlinearly realized symmetry, it'd just be a bit. And you also, from that point of view, it would look like if you just were trying to write the standard model directly in the physical vacuum, for example, it would look like the coupling between the fermion and the Higgs being the same, set by the same parameter as the mass of the fermions would look like an accident. You could accommodate it, but you wouldn't explain it, right? And so right, that's the kind of freedom that HEFT allows us, is that we can just change those parameters freely, nothing stopping us, right? But there is a parameter point in this description, which is the standard model. No, because there, if I have any deviation from the standard model, right, that tells me there's new physics. I mean, the standard model is not the complete picture. So if I want to write down the full UV completion, if I fail, certainly, right, the standard model is a subset of SMEFT. So if I fail any of these criterion, then I know there's new physics. Okay, so let me give you the simplest example we could cook up. After all, you know, the people, great people in my collaboration are, you know, we're all really model builders at heart. And so, you know, one of the things we bring to this subject is thinking about what is the EFT really telling us about the UV completions, okay? And so you know, so far in these lectures, we've only been talking about the low energy description, but now I want to write down a simple UV completion, and I'm not gonna do the matching calculation. There's some details in the paper. It's a good exercise. This one's just a tree level. So it's pretty straightforward, a bit tedious, but straightforward. And then I'll just give you the sort of EFT that emerges, okay? So let's just understand this by example. And by the way, everything, I mentioned this in passing a few times, but I just want to emphasize, especially now that we're getting into sort of the punchline, is that everything I'm going to tell you is about perturbative UV completions, okay? Where I write some perturbative new physics at scales above the electroweak scale, okay? In principle, there's also some non-perturbative stuff that could live here, okay? This criteria should still hold, but I don't know how to calculate anything, okay? So just keep that in mind, is that I want to give you sort of the two perturbative cases where this criterion can fail, okay? But of course, there's some world of non-perturbative theories that also could live in this band, and I just don't have anything useful to say about them. Other than the fact that I think they're unlikely to exist in nature, just because, you know, as the LHC keeps running and we sort of see that there's no new physics near the electroweak scale, there really were a bunch of strong dynamics, right? I mean, I think the best case scenario is that the Higgs is potentially composite with a gap, right? And we have this whole framework of composite Higgs, or the strongly interacting light Higgs, this, you know, work, this Silch paper, very famous paper that Alex actually co-authored. If you don't know about that, that's something definitely, if you're interested in this stuff, that's something to look at. Okay, so let's get into an example. And in particular, like I said, I want to focus on the criterion that this condition fails. Okay. So let's take a extension of the standard model by a singlet scalar. And let's integrate it out at tree level. So here's the UV model. We have LUV is DH squared. Remember, again, we're only focused on the scalar sector, so. Okay, and then all the interactions are just in the potential. So we have V is minus UH, H squared plus lambda H, H to the fourth plus 1/2 M squared plus kappa magnitude H squared, S squared plus 1/4 lambda S, S to the fourth. Okay, so just a, you know, normalizable UV model with, right, the Higgs is going to get a VEV, setting the Higgs mass parameter negative, and I have this interaction with the singlet, okay? So I'm imposing here a Z2 symmetry on the singlet, okay? So then we can just integrate this out at tree level. Notice that having some tree level interaction requires the singlet to get a VEV, right? So really I have this term is generating some, vertex, cubic vertex with this singlet, and so that's really what's being generated here. But I'm going to use functional methods. So which is just at tree level fancy terminology for saying we're going to use the equations of motion. But maybe as an aside, this is something that I've written a couple of papers about and appears a lot in this SMEFT enough paper, which is that you can also apply functional methods. We now know how to do it at one loop, and even there's work pushing it beyond one loop. And basically, right, there's this universal log determinant form that shows up at one loop, and our team and others have come up with a systematic way of evaluating that. And at this point, it's essentially automated. We have a little bit of code, but actually there's much better codes than ours. But in the paper, here I'm going to focus on this tree level example, but in the paper we apply this also at one loop to show that all the same conclusions hold, okay? And you can see this actually lets us do calculations that you wouldn't be able to do by just matching diagrams. Okay, so we're going to use, right, this is just use the equations of motion for the singlet. And what we get is what I'll call L effective, relatively standard terminology. This is not the EFT yet, okay? And I'll explain why in a moment. Let me just write the formula. H to the fourth plus 1 over 4 lambda s. Okay, so yeah. So as I said, S needs to get a VEV, right? So when S gets a VEV, this gives you, yeah. And when you use the equations of motion, it sort of automatically incorporates that possibility. Okay, thanks. Yeah, I just want to take a moment to explain why I'm not calling this the EFT, okay? So this is not and that's because we have field dependence in the denominator here, okay? So again, what this functional approach lets you do, if you were just matching diagrams, you would be working order by order in the fields and the derivatives, right? But if you use the equations of motion, it gives you a little bit more. In this case, and in the one loop cases that we looked at in the paper, you get sort of all order results in terms of the field space, okay? And this is going to be important for evaluating this criterion, okay? As you'll see in a moment. But I just want to emphasize, right, because I've been saying it over and over and over, is that an EFT is a local expansion in fields and derivatives, and it's truncated, okay? Because you have to impose that you're working to some order in your power counting. Here, right, I have not truncated in the fields. Right? I have this resummation. Okay? So in our paper, we we tried to be very careful to distinguish the effective Lagrangian, which is the low energy description in terms of H alone, from the EFT, which is then expanding and truncating this result. And one thing that I just want to highlight here is that at tree level, this actually contains the entire dynamics of the UV theory if all you're looking at is, say, the scattering of H particles, little h and n, or pi, right? The Goldstones and the physical Higgs, because you've used the equations of motion for the singlet, okay? So we've made this assumption, we've eliminated the singlet from the external state, okay? But we're solving the path integral here, and so this is actually encoding the UV, okay? So again, it's not an approximation. It's a tree level approximation, but it's not an EFT approximation yet because we haven't truncated. Okay? So this is a tiny. It seems like a tiny point, but it's actually very important conceptually for the bigger picture of just understanding what EFT is about. Okay. All right. Yeah. Yeah, so I'm only working to two derivative order here. Okay, right. Good, thanks, yeah, exactly. Right, so I'm working to all orders in the fields, but two derivative order. Again, because I'm trying to make this connection with geometry. Okay, so now we just take all of the formulas from previous lectures. We want to take this Lagrangian in terms of big H. We want to express it in terms of little h, and do I use n or pi here? I don't even write it explicitly, I guess. And the Goldstones, okay? Then we want to identify K and F, okay? Because then we can use them to construct R, right? Because, I don't know, 2 or 3 lectures ago, I wrote a general formula for R in terms of K and F, right? Where I identified the metric in HEFT, and then using the metric, I turned the GR crank and computed the Ricci scalar. Okay, so, which again, if you're interested in this stuff, that's a very good exercise to go and do. Okay, so we express this L effective in terms of H and N vector. We identify K, F, and V, and then we compute R, and what we get, well, here, I'll tell you what K, just give you this one intermediate step. There could easily be typos here. Okay, the formulas in the paper are almost certainly right, thanks to my very careful collaborators. Okay, V times F of H is just V plus H, and the potential V is minus a half mu H squared plus a quarter lambda H V plus H to the fourth minus 1 over 16 lambda S 2m squared plus kappa V plus H squared. Okay, and then from here, we derive R. So we have 6 over V plus H K cubed DHK plus 6 over b plus h squared, 1 minus 1 over k squared. And this is 3 kappa squared, 2 kappa v plus h squared, kappa minus 2 lambda s minus 16 m squared lambda s over kappa plus h squared, kappa minus 2 lambda s 4 m squared lambda s all squared. Okay, and here I used that DHF is 1 over v and d squared HF is 0 in this example, right? Just because f is so simple. Okay. Right, you can see this is trivially follows from here, okay? Again, all these things today are up to, getting stuck in little algebra. It really should be like an hour or so of work to just sit down and compute. And I highly recommend you check so you really see how all the moving parts work. Okay? So now we have an expression for the Ricci scalar in this theory. So let's check all the criteria. So f of h star equals minus v equals 0. Does that exist? Well, pretty obvious that that exists, right? So we're good. Then the second criteria over there, right, is Taylor expanding about v, okay? Sorry, about minus v, But if you look at this, at these formulas, yeah, there's some, oh, I'm missing parentheses there. Let's see. Just by, okay, this is a polynomial, it's obviously fine. This is obviously fine. Here, there's this thing in the denominator, but there's these other terms, so there's no obstruction to Taylor expanding this. Okay, so this was A, I guess. B, Taylor expansion looks fine, right? No problem there. And what about C? So let's evaluate R at H star. So we just take this formula, plug in H equals minus V, okay? And we get minus 3 kappa squared over m squared lambda s. And this is finite. Okay, voila. I live in France now, so I get to say that. We have SMEFT. Okay. I mean, no, this VEV is the VEV of the Higgs. No, we've integrated out the singlet. So all the mixing effects and so on are captured by the effective theory. But it's all expressed, right? There's no singlet anymore. But that's all consistently incorporated when we use the equations of motion. Yeah. So these parameter choices are being made here, right? I mean, the m squared and lambda, right, and kappa, these are all parameters that are connecting the singlet, that depend on the singlet, right? So if you worked in the full theory and you indeed incorporated all the mixings and so on, right, the claim is that that's all just consistently incorporated in using the equations of motion. That's the magic of using the equations of motion, You don't have to be careful. You just, right? That's my, I think, you know, I'm a simple guy. Like, to me, diagrammatic matching is very tricky because you have to be careful with all these things you're worried about. You just use the equations of motion. You don't have to think. You just turn the crank. And indeed, these functional methods at loop order, I mean, it's not trivial. I mean, it's loop calculations, but it's similarly, that's why automation of this, well, people have done actually, people in the room have done automation with diagrammatic matching, but with this functional matching, the, sorry, that's I'm misremembering. Joydeep's thing also uses functional methods, but the, if I remember correctly, but the, but this is really amenable to automation, and there's this whole business of the universal 1PI effective action. Again, that's using these functional techniques because you can kind of compute things once and for all. You don't have to be clever. Okay, so here we are. We have the curvature evaluated at the origin. It's perfectly finite, okay? So when we have this theory with all these parameters turned on, SMEFT exists in the sense that we can, you know, take these objects, we can Taylor expand in little h, we can truncate. We have a perfectly well-defined effective theory, okay? Yeah, we're gonna talk about special points in parameter space next. Yeah. Right, but the generic parameter space, there's no obstruction to writing SMEFT. If all this stuff's turned on, then we're happy. Okay. So just to make that super concrete, maybe over here, let me just write explicitly what that SMEFT Lagrangian looks like. Okay, so we have L SMEFT is dh squared plus mu h squared h squared minus lambda h fourth plus 1 over 4 lambda s m squared plus kappa h squared squared minus 1 over 8 kappa squared over lambda s m squared d h squared squared plus dimension 8. Okay, so the, what do I want to say? I mean, we get, just as expected, right, in any matching calculation, you know, we get corrections to the dimension 4 terms, right? That's here. So we need to redefine what we mean by the mass squared parameter and the quartic in, at low energies, as all, you know, as we always have to do in EFT. That, by the way, is the connection to renormalization. It's exactly the same idea, right? We redefine our parameters at low energies to incorporate UV physics. That's what renormalization is all about. It's just EFT, okay? But here we generate some dimension 6 operator suppressed by a heavy scale, okay? So it's everything it's supposed to be, okay? This m squared parameter is setting this cutoff for the EFT, right? The scale of new physics. No surprises. Yeah, but the problem with that kind of argument is that it's field redefinition. It's not field redefinition invariant. Yeah, but that's exactly the point of this simple case. Is absolutely everything you say is correct. But so it's sort of a necessary condition, but not sufficient, right? Because I can do field redefinitions, and I can, as I've been, you know, showing, emphasizing over and over, right? I can completely obscure that by right. The point is here, because what I did is I really did the calculation matching already onto the SMEFT-like description. It's in a nice basis for SMEFT. But if I did the matching directly to HEFT, and then I asked, can I go to the, right? If I hand you, the whole point is if I hand you the HEFT Lagrangian, right, can you go from that to SMEFT? And that's where it gets nasty, where the field redefinitions can really bite you. Yeah, so I mean, I expect everything today to be, I hope, extremely intuitive, especially given how much you've learned in the last 2 weeks about EFT. Okay. So all these questions, I mean, you're all anticipating exactly where we're going here, which is that it's kind of obvious. I mean, Rick's question there, again, it's kind of, you know, he's anticipating that you look at this, right, and what we're doing to derive that formula is just expanding this smaller than this, right? Well, what happens if we set the mass to 0? Then it's all of a sudden there's no expansion to do here, right? You have something that looks genuinely non-analytic. So that's exactly what we'll do next. And of course, the expectation is that this criteria had better fail, right? It better tell you that you can't do the expansion if you take that point in parameter space. Yeah, let me come back to that question. I mean, that's kind of going to be one of the main points I want to make. But let me. So all I'll say at the moment, and then I'll try to really emphasize the answer to that question is yes, in the sense that I'm welcome to do this, right? Nothing's stopping me. The question is, does it generate an EFT or not? Okay. I can do this. It may not be useful. That's really the point. Okay. Yeah, that's going to be the point. Yeah, exactly. Okay, so let's talk about this point with m squared equals 0. So now we can be a little bit more careful with the evaluation of R. So let's first take m squared equals 0 in the formula. Okay, so this is just taking that R formula, setting m squared to 0. And then if I send h to minus v, then these are full of typos. There's a mincing minus sign there. If I send h to minus v, okay, then clearly I get infinity. Okay, so criteria C fails. And HEFT is required, okay? So what's the point? The point, it was kind of already said, is that if I'm working in SMEFT and I have, you know, I erased the UV theory, but you can see it here, right? And I set m squared to 0, then what I've done when I'm working in the theory evaluated at the origin of field space at H star, okay, the O4 invariant fixed point, well, then without this m squared, right, I have something non-analytic. What did I do? I integrated out a massless particle, right? So this criteria is failing because of exactly this fact. I integrated out a quote massless particle, and oops, the particle's not in quotes. I put the quote in massless because, of course, when I go to the physical vacuum, the particle I'm integrating out gets a gets a mass from the Higgs VEV. Okay, so it is a massive particle, and I in principle can integrate it out self-consistently. So if you don't know this, maybe you heard this from, say, doing Coleman-Weinberg calculations or some example like that. You know, you generate non-analyticity when you integrate out massless states. You can integrate them out. It just makes your theory non-analytic and non-local. What's the physical interpretation? It's that, you know, so the only time we can do this EFT expansion where we're shrinking propagators to points is when they're heavy, right? And we don't have long-range interactions. As I sort of stretch out the propagator, right? I separate the effective vertex into the more fundamental vertices. I get an exponential suppression as a function of the distance, right? It's a Yukawa-like potential. If I have a massless particle, it's a long-range force. And so maybe you knew this. If you didn't, it's one of the interpretations of finding non-analyticities, if you're doing some calculation, is it's a sign that there's some new massless degree of freedom that you should have incorporated in the theory, and you should go looking for that, and you should look for a UV completion, okay? So in this completely simple, stupid example, that's exactly what's happening, right? Again, when I'm evaluating at the unphysical point in field space, the origin, right, where I like to do model building, but HEFT exists because HEFT is the expansion around the physical vacuum. And in the physical vacuum, this particle gets a mass. And so it's perfectly consistent to integrate it out, okay? So that's really, when I say, this question, when is HEFT required? What theories live here? Well, this is a class of theories. And again, we have one loop examples and so on, fermions, it's all the same. This is a class of theories where the particle gets all of its mass from electroweak symmetry breaking. That means that the SMEFT version of such theories has a massless particle in it, okay? And that's really the big, that's one of the two cases that we're able to identify with these criteria, and that's kind of the big point of today, okay? No criteria fails, but I'll come back to that point. SMEFT is useless. It exists, but it's not helpful because it doesn't converge. But yeah, that'll be one of the points I make at the end. But from this sort of technical point of view, right? If I haven't defined SMEFT by physics, right? I've really been very sort of I haven't worried about what I'm doing with this effective theory. I've just asked, can I write a local expansion, right? Correct, there's no symmetry that forbids the mass term. Oh, I'm not worried about the properties of this model. I'm just trying to understand what's the, yeah, absolutely, this is a special point in parameter space. In the paper, we do a fermion example. If you like that better, again, that mass is protected from quantum corrections. But yeah, you're absolutely right, but I sort of don't, right? I don't care for the purposes of just understanding what are the theories that live in that band. Okay, any other questions? Good, maybe I'm okay with time. So yeah, I just want to then, this is kind of the main physics result today. Now I just want to kind of summarize and talk about the big picture and then come back to this question that Rick asked. So, and this has already been anticipated, okay? There are basically two classes of models, again, restricted to perturbative UV completions, where we can see that this set of criteria fail, okay? So let's just review that. By the way, if you could find a loophole to this, you should write a paper about it, you should tell us, we'd be very interested. I can't think of anything else. But that doesn't, of course, I mean, it could exist. And there's, there's another game, again, this I don't think is necessarily worthy of, there'd have to be more than this to write a paper about it, but there is something that we kind of argue for in the paper by just sort of by example, is that this leading order criteria is enough. This is all you have to check. But of course, yesterday I showed you that the real criteria, the robust one, has there's sort of an infinite number of things you need to check. So there are likely pathological cases with multiple particles in the UV and very tuned couplings where maybe R is finite, but the covariant derivative, the first, say, covariant derivative squared of R is not, or well, if, yeah, I mean, for example, if the zero doesn't exist, then you can't ask the rest of the questions. But these are not field redefinitions. So K and F change under field redefinition. The whole point of using geometry is that I don't have to worry, right? So I have K and F, I might as well evaluate the thing that's invariant. Because again, I showed you, right, in the, that the, here I've evaluated, but if I do field redefinitions on little h, it makes non-analyticities in big H, right? So yeah, field redefinitions of little h will keep everything analytic in little h, but if I do field redefinitions in one and not the, the whole thing is a mess, right? This is why we argue that you need to frame this in terms of geometry, okay? So, I just want to spend our last few minutes together talking about the physical interpretation. To me, this is the lesson that we learned is that there are two ways that SMEFT can fail. Again, this is all in perturbative examples. I think it's in the world of strong dynamics, almost certainly there are other cases. They probably, frankly, they probably fall in these two classes, but I can't prove that to you. So the two ways are, one, there's no O4 invariant fixed point right? So in my very loose analogy with the black hole, that's like saying there's a horizon, right? There's this point you can't go past. Again, very loose analogy. And that means that there's the physical interpretation is we have additional electroweak symmetry breaking. So I didn't have time to work out to show you one of these examples because I also think it's extremely intuitive. It was anticipated from almost the beginning. But nonetheless, if you're curious, we have a whole long discussion of this in the paper. We do this really nice toy example with just an abelian model with two fields where both of them get VEVs, and then we show very explicitly how this leads to the lack of an O4 invariant fixed point. And you'll see all these nice pictures of field space manifold, plots of field space manifolds, and so on. There's tricky business in there, but I leave those details to the paper. But physically, right, this is just saying that there's no point in the manifold just expressed in terms of the Higgs where electroweak symmetry is restored. So there must be another source of electroweak symmetry breaking. Okay. So that's simple. And then now we've seen maybe a slightly less trivial case, which is that the curvature at the fixed point is infinite. And this corresponds to the physical case of we integrated out a state that gets all of its mass from the Higgs. And again, now I'll just say it for like the third or fourth time, right? That means that at the origin of field space, what we did was we integrated out a massless particle who only gets mass when we go to the physical vacuum where it's legitimate to integrate it out. Okay? So the real lesson is the whole point at some level of the HEFT description is that it describes non-decoupling new physics. So again, this is something potentially interesting that, that we never really worked out, is, of course, HEFT incorporates SMEFT. So when I use this phrase non-decoupling, what I mean is I've taken the parameter that allows me to decouple this particle by making it arbitrarily heavy, and I've set that parameter to 0. So now the only way I can make this particle heavy is by cranking up its coupling constants, and we know, right, that those can only be order 4 pi, whatever exactly the unitarity bound is, right? But those cannot be arbitrarily large if we're talking about a perturbative model. So there is an upper bound on the mass of this new physics state. It's of order the weak scale times some big coupling maybe. And so that's the sense in which it's non-decoupling, right? There's no way I can make it arbitrarily heavy in this theory since I've set the mass parameter to 0. Similarly, with extra electroweak symmetry breaking, in that case, if I have some new physics that has a small electroweak symmetry breaking contribution, well, once it has that VEV, if I fix that VEV, then that's fixing essentially the mass scale in the UV theory, and I can't decouple it anymore. Again, it's going to be like the Higgs mechanism in the Standard Model. Once I've set the VEV to 246 GeV, then I can't make the Higgs boson arbitrarily heavy, right? Because the Higgs boson depends then on, well, it depends on how you write it, right? But the Higgs boson is coupled to V. I can make the Higgs as light as I want, but I can't make it heavy, arbitrarily heavy, right? So in the same sense, if I added a second, say, Higgs doublet, or I added a Higgs triplet, okay, these are things we again talk about in the paper, then that's another example of a way we could have non-decoupling new physics by adding new perturbative states. As an aside, it turns out the Higgs doublet example is quite complicated to the point that actually we wrote a whole paper about it recently. It's not so much, in that paper, the geometry is not so important, but we were very informed by having done this study. If you're curious, you can go check that out and see what kind of, again, it's all this field space manifold mixing and so on. But the case of a triplet or some other representation breaking electroweak symmetry is more straightforward. Yeah, so then there's a runaway direction for the VEV of S, right? It's not going to be a consistent parameter space because remember, S is getting a VEV, so it needs its quartic to stabilize it. Yeah, so you can't set that quartic to 0. Yeah, that's a great question, right? There's some additional UV information encoded there for sure. Well, I think you'd want to be careful. I would want to be careful about the order of limits here, right? In deriving this formula, I assumed it was non-zero. I think you would find an obstruction before you would get there, but yeah. So I didn't write all the steps, but I think you would see that you need that quartic. Yeah, I think even when you're just trying to write L effective, you'd probably see the problem at that point. That's my guess, but because this really wouldn't be self-consistent yeah, just because you need the quartic to stabilize the VEV, it would be a runaway direction. I think you would see that in the derivation. Okay, so ooh, geez, Another point, I want to make a couple more points. I'll try not to go too far over. So one thing to notice about HEFT, when you write the HEFT description, this idea that it's sort of non-decoupling, that's its purpose in life, okay? So even on the first day, right, I was talking about the fact that the SMEFT expansion and the HEFT expansion are different organizations of the operators, right? And I gave you this example of just the Higgs potential, right, having the fact that the cubic and quartic and so on are all independent, whereas in the SMEFT description, they're correlated. Well, that's really, what HEFT is about. HEFT is about accommodating the situations where you have this non-decoupling new physics, okay? Because there is a self-consistent low energy theory, okay? It's just you can't use the more theoretically appealing description in terms of expanding around the origin of field space. But of course, because HEFT includes SMEFT, HEFT should also have some memory of the decoupling properties, but it's all scrambled. And so we never really disentangled that. That's something maybe interesting, is to understand if there's a way to frame HEFT in a way that's sort of manifestly decoupling. I don't know how to do that. I don't know if that description exists, but it's good. Thank you. That reminds me that I wanted to emphasize, this is why I was talking about this sort of effective Lagrangian versus the EFT Lagrangian, because to evaluate this, you need the all orders in fields. You need the result to all orders in fields. If you do the expansion and work with the EFT Lagrangian before you compute R, you won't actually see this singularity. So I don't think there's, my strong intuition is that there is no way we'll ever know the difference between, there's no way we'll know if HEFT is required from low energies. So, so to me, what this motivated was one of our, and again, we kind of followed through with this. So we had one of our later papers where we added Ian Banta, Nathaniel's great student, was to actually try to classify, with always some caveats, but we covered a huge space of models, all possible consistent UV completions where we add one new particle that gets most of its mass from the Higgs and has this sort of non-decoupling character, to explore whether or not there's any parameter space open for non-decoupling new physics. Because intuitively, what this is telling you is that you've got a state that's near the weak scale, couples to the Higgs, so likely we can probe it. And in fact, we found very few models that are still phenomenologically consistent, that aren't ruled out. So there's a couple of pathological or kind of edge cases, a pure singlet scalar, we all know that's really hard. And indeed, in the paper, we see that case still has some open parameter space. But there aren't very many. So so to me, to kind of answer that question from a phenomenology point of view, the strategy that we think is most effective is build all the UV models. There's only a few that are left, and then you have concrete targets, right? So you can really, from the UV point of view, you can rule out HEFT, right? In the sense that if there's no perturbative UV completions, then you know that SMEFT is covering all of the at least perturbative possibilities. So that's kind of the strategy that we're pushing for. Okay. No, more what I mean is that, so from a phenomenology point of view, the difference, I would say the difference between SMEFT and HEFT is that SMEFT has extra correlations, right? But, so I think the Higgs potential is a great example. In SMEFT, if I truncate at dimension 6, then there's only 3 operators, right? The mass squared, the quartic, and the sextic. But when I expand in the physical vacuum, I get a cubic and a 5-point vertex, right? And so there's more couplings to measure than free parameters. But that's because I truncated at dimension 6. If I go to dimension 8, now I can fiddle with, right? I have more free parameters. Yeah, but if lambda is small enough, I mean, and anyway, I can make coefficients arbitrarily big. I'm just saying I can accommodate anything I want, order by order in SMEFT, unless you measure absolutely every point function, right? You really need to do an infinite number of observations. So yes, as data gets better, and of course it's hard at the LHC to go. Yeah, but I can have an accidentally big, coefficient at dimension 8, right? So you can't ever exclude, and at some level it's sort of, So so to me, the whole purpose of this is to, if we're telling our experimental friends to do something, typically, right, we're always telling them to do things that live here and the interpretation is here. And we can argue about whether or not, how useful any of the phenomena, the phenomenology is a whole other thing. That I can complain for hours about the way things are done. But, and I disagree strongly actually with a lot of what's being done. Nonetheless, to me, all that matters from the phenomenological point of view is that we are looking in every signal region where we might find new physics, because it could be there, we need to look. When we organize our thinking about where to look and what to prioritize with SMEFT, right, that's a UV hypothesis. And we typically make this assumption that you're making, right, that you're pointing out, that dimension 8 is smaller than dimension 6, which is very reasonable because SMEFT is this description of decoupling physics. But, a good experimentalist would worry that, theorists have led them astray over and over. We keep telling them to look places for new physics. They're not finding it. So, they might hear about that there's this more general description, and then they might worry that, oh, well, we've been missing things because we're not thinking in this more general framework. And so that was really my motivation, I think my collaboration's motivation for this whole exploration, was to understand, are we missing something, right? Is there something that lives in this band that's still viable, that by biasing ourselves, by thinking that new physics is heavy, right, so that it's in this decoupling limit, using SMEFT as the theoretical tool, that we would be missing something, okay? To me, whether or not it's SMEFT or HEFT, I mean, ruling out this band, I think, is actually something that the FCC folks have kind of latched onto because it's something they can do, right? And in fact, there are general arguments. We made one in this unitarity violation paper that the theories that live in this band all will violate perturbative unitarity at order 4 pi v in some process. So in principle, you would see, if you really are living here, I think you would be able to see that, maybe not at the LHC because it's, this precision stuff is hard, but if you went to FCC, you almost certainly would see signs of deviations because HEFT is non-decoupling and you're probing the electroweak scale up to 10 TeV and you're doing a lot of precision measurements, you'd almost certainly see something. Anyway, it's really, I think, the point I want to leave you with is that if you're somebody who's gotten into HEFT, you're doing some hard calculations within the EFT, okay? I hope you'll go home now having a better appreciation of the kinds of theories that you're probing, right? Why are you working with HEFT and not SMEFT? SMEFT is still hard, but it's easier to work with. Well, that means you're whether or not you've realized it, that your UV hypothesis is that you think non-decoupling new physics is worth the effort, right, to understand in this EFT language. I'm already way over time. There's one more important point I wanted to make, and I've said a lot of this already. You can read, I sort of wrote some outlook here and stuff, but I want to come back to very quickly, I'm only 5 minutes over. Okay, so I want to come back very quickly to this point that Rick was making, which is that everything I've been talking about here has been sort of very formal, okay? I just wanted to know, I hope I've been really clear about my, what I'm asking, okay? I've really tried to frame the question carefully. And so this question of SMEFT exists, HEFT exists, is all about just whether or not I can write a local expansion, okay? But then immediately you should ask, well, is it useful, okay? And the answer is actually that not necessarily. So, right, it seems like what I've told you is, okay, so you set m squared exactly equal to 0 in this model that I was presenting, then you're forced to use HEFT. What if it's epsilon? What if it's tiny? it seems weird that now all of a sudden you can use SMEFT and not HEFT. Like you can make it arbitrarily small. So something seems off about that, right? Well, the answer is that really this criteria, while I think it was correct, as stated, it's not really physically the right question, okay? Physically the right question, this is what we call in the paper the practical criterion, is whether or not your EFT expansion converges. Is it useful, right? If you want to go make predictions at dimension 6, is the dimension 8 term small? It's related actually to the conversation we're just having, right? So the real answer, what I say, what I've said in print, is that if I want to use, if I have a light particle that gets most of its mass from the Higgs, where you can make that most precise using all this stuff, but it doesn't matter, like order half, roughly half. If you have a particle that gets half of its mass from the Higgs or more, then it's pretty easy to show through these matching calculations that the SMEFT expansion doesn't converge. Okay, you need really high orders to get some, so that, what do I mean by converge? I just mean that I work at dimension 6, I compute, say, the Higgs cubic coupling in the effective theory. Then I add dimension 8. Did it change by order 1 or did it change by a tiny amount? Well, basically, the point is that you're really doing, in the physical vacuum, you're doing an expansion in V over the cutoff to some power. So if this effective cutoff is smaller than V, which it can be, if I take my singlet model and I give its m squared just a tiny amount, 1 GeV say, well, then none of my observables are going to converge in SMEFT. Okay? So SMEFT exists in that I can write the local expansion, but it's not really useful. I really need to use the HEFT description. Okay? So that kind of answers what might have been this issue that might have been bugging you a little bit, which is that really to be physically relevant, I should add an extra line to the criteria, which is that once I have this expansion, that the power counting helps me, right? In other words, said in a really more EFT way, right? EFT is useful when the power counting parameter is a small number, so I can do perturbation theory in it, right? So that's, I think, the ultimate lesson here is that HEFT is the description that you have to use if your new physics is non-decoupling, and this sense of non-decoupling is really that it gets most of its mass from the Higgs, or that it generates a new source of electroweak symmetry breaking. Okay, those are the sort of two cases. And again, there's probably more to do in the phenomenology. I mean, we classified some big set of UV completions and investigated them, but I think the question of can we rule out all the models that live in that band is still needs attention. And by the way, we just showed that the parameter space exists. We didn't do the study to show what it takes to close it. Okay, so I think there's lots to do in phenomenology. There's lots to do in many directions here. Anyway, I hope that this has been useful for you. It's been, like I said, it's really been a privilege for me. And if nothing else, maybe now you have a little bit more insight when you're thinking about applying EFT for BSM. You have hopefully a little more context and insight into what you're assuming. Okay. Thanks again for your attention. I'm happy to take more questions, to chat over coffee, and again, just to say thank you to the organizers. This is an amazing thing you guys got to experience here. They really brought in exactly, I think, the topics I would have chosen. I mean, I really think they did an incredible job, and I know you know how lucky you are to be here. I can tell by your enthusiasm. And so yeah, I really appreciate your attention and everything. And I won't be here tomorrow, so please make sure if you want to chat to corner me today. All right, thanks a lot. Yeah, good. So if you're in this case where you have some non-decoupling particle, then we showed actually in the second paper in our series that you violate perturbative unitarity in processes that are like basically pi to n Higgses, where n is order 5. We were able to use these geometric tools to compute the amplitudes for pi to any number of Higgses in the high energy limit and phrase it geometrically. We also did 4 pions in a number of Higgses. And that allowed us to test perturbative unitarity. And actually, I don't think I cited it in my references, but there's a really nice paper by Adam Falkowski and Riccardo Rattazzi. They called it Which HEFT. It's a short, quick read. It's really good. Our paper is basically that idea in sort of the full using they give some correct arguments for that are very closely related to this about non-decoupling and so on, and the correlation between having non-decoupling new physics and unitarity violation at 4 pi v, and we just sort of made that rigorous in our paper. But what we find, if you look there, there's just a plot where we show that in one of these non-decoupling examples, I think it was this one with the singlet. Actually, I think it was the one with the singlet at loop level, but whatever. In one of these non-decoupling examples, that the amplitude for longitudinal W scattering to Higgses saturates 4 pi v very quickly when you go to 5 Higgses or something. So you know that the theory doesn't make sense past 4 pi v, which is really the expectation, right? If this thing is, when you're in this non-decoupling regime, then HEFT is truly a nonlinear sigma model, and nonlinear sigma models, right, have the cutoff at 4 pi f, right? 4 pi v in this case. I should also say in that paper, this is due to brilliance of Dave Sutherland, he realized that we could use these, this field space geometry picture and apply, so in order to understand the sort of convergence properties and so on, we apply this old theorem, this Cauchy-Hadamard theorem about radius of convergence in terms of like, it's this very cool theorem. If you don't know this, you should go look it up. I didn't know it before we wrote this paper. But basically, you can relate the radius of convergence of a series to its analytic properties. And so one thing we can see is, I guess it's not up here anymore, but when the mass of the singlet, even if it's not, so when the mass of the singlet is 0, there's clearly a singularity. But when the mass of the singlet is non-zero, you get a singularity in the complex plane. And so the Cauchy-Hadamard theorem covers that case. And so we can actually show that when you're in the parameter space where HEFT is non-decoupling, you get perturbative unitarity violation at 4 pi v. It's very satisfying. It works exactly as, like intuitively, that's what the, Ricardo and Adam said, but then we actually can show it rigorously in this paper. I think it's a really cool result. So yeah, it's, but then if you're outside this decoupling regime, right, if the m squared parameter is big, now you're in the parameter space where SMEFT is allowed, and so you should see that actually the cutoff of HEFT is secretly this much bigger scale. And indeed, you can see that if you take these UV models and kind of apply this technology that we developed. And so, yeah, so it's super nice. Everything works exactly as it should. Non-decoupling stuff, cutoff is 4 pi v. Decoupling stuff, the cutoff is the BAS associated with that new particle. Thanks again, everybody.